Welcome! In this video, I'll show you how to solve problem 6.31 as it appears in the third edition of Griffiths Introduction to Quantum Mechanics. Now, the problem states the following. It says, when an atom is placed in a uniform external electric field, the energy levels are shifted, a phenomenon known as the Stark effect. It's quite similar to what we had with the Zeeman effect, except this is now basically the electric field version. In this problem, we analyze the Stark effect for the n equal 1 and 2 states of hydrogen. Let the field point in the z direction so that the potential energy of the electron is what we have right here. So basically minus E times the external electric field times R cosine theta. Treat this as a perturbation to the Bohr-Hamiltonian. Spin is irrelevant to the problem, so just ignore it. A. We want to show that the ground state energy, there's an E missing there, is not affected by this perturbation to first order. Then B, the first excited state is fourfold degenerate. Using degenerate perturbation theory, we will then determine the first order corrections to the energy. And then we want to know into how many levels does the energy split into. C is what are the good wave functions for part B, and we want to find the expectation value of the electric dipole moment, which we have right here, minus ER, in each of these good states. Notice that the results are independent of the applied field. And we will then note, of course, that hydrogen in its first excited state can carry a permanent electric dipole moment. All right, so let's do this by part. So we now have to deal with the Stark effect. If you don't really know what it is, beyond making the analogy with the Zeeman effect, it is not too relevant for this problem since we have to apply, this is basically just the application of perturbation theory. So this right here is going to be our perturbation, and the unperturbed states, as I mentioned, will be the Bohr-Hamiltonian, but without taking into account the spin interactions. Okay, so if we want to find now the correction to the ground state, basically the energy correction to the ground state, well, then we need to begin by taking the expectation value in the ground state. So I just wrote down all of the, wait, there we go. Oh, I moved that. I wrote down all of the wave functions that we will need. We have already seen how to calculate them in the first series of lectures. And there's not really much point in calculating them now, so I'm just going to refer to them. So in part A, we want to find the energy, right? So the first correction to the first energy level to the ground state, which is going to be psi 0, 0, sandwiching our Hamiltonian, psi 1, 0, 0, right? This is as usual. This is simply perturbation theory. And of course, we can do this because the first state, this is not degenerate, right? Okay, so we are using non-degenerate perturbation theory for this part. And that says, of course, that the energy level, the correction will simply be the expectation value of the perturbation with our wave functions. Okay, so let's calculate this. So psi 1, 0, 0 is what we have right here. This right there. So let's use it. So we're going to have this thing squared. So we get 1 over pi a cubed E over minus 2r a. Of course, we are going to be integrating over all of this. And then we, of course, cannot forget about the perturbation, right? This Hamiltonian, which is minus E, the charge of the electron, external field, R cosine theta. So it's going to be minus E, external field. I'll just write it as big E, no need to write the EXT, R cosine theta. And since we are integrating in spherical coordinates, do not forget, and I cannot stress how important this is, do not forget about r squared sine theta. And this is going to be integrating over the r, the theta, and the phi. Now, in problems such as these, I always recommend doing the radial integral last. Why? Because many of these integrals could be 0. And the radial part is rarely 0. So for that reason, if we do r first, we will always have to do that integral. But if we do theta or phi, there could be cases where the integral is 0. So, why bother? So for that reason, in this problem, we will always do either theta or phi first. Now, in this case, we can see there is no phi dependence. So for that reason, it's impossible for, for that to be 0. So we can just integrate it right away. We'll get 2 pi, right? Because we're integrating phi from 0 to 2 pi, so we just get 2 pi. So this will be 2 pi times this, so the pi's cancel out, and we get 2 over a cubed, a minus sign, small e, big E. I think that's all the constants. And then integral e minus 2r over a, and then we have r cubed sine theta cosine theta, right? I'm just doing a naive approach to this problem. Now, which integral should we do next? Well, I mentioned r is what we want to do last. So let's go for the theta integral. Let's take a look at that. So the theta integral, this part right here, it's going to be integral from 0 to pi of sine theta cosine theta d theta. All right, and we can rewrite this. We can rewrite it as 1/2 of the integral from 0 to pi of sine of 2 theta d theta. And this is, of course, going to be minus 1/2 cosine evaluated of 2 theta, evaluated between 0 and pi, which is going to be minus 1/2. And then we get, it's going to be 1 minus 1. So 0. So here we just checked, we verified that the ground state energy is not affected by this perturbation. All right, so there is no correction to the ground energy. Okay. Now that is part A. Okay, so all we did was just take the energy correction, as we have done many times before. There wasn't anything particularly new or weird about what we did. Now, part B. The first excited state is fourfold degenerate, right? So the first excited state is this right here. We have 2, 0, 0, 2, 1, 1, 2, 1, 0, 2, 1, minus 1. So that's the first excited state. And we want to now use the degenerate perturbation theory to determine the first order corrections to the energy. Okay, so basically into how many levels will our energy split. So now we will do, what we have been doing in the past. So how do we find energy corrections in the degenerate perturbation theory? Well, I hope you recall, it's by finding our beloved W matrix, right? And then finding the eigenvalues of the W matrix. So this was a matrix that was W11, W12, W13, W14, and so on and so forth, right? 2-1, 2-2, 3-3, and 4-4 in this case, right? And of course, other terms. Sorry, I'm getting over a flu. Okay, so we need to find each one of these elements, which is going to be a bit of work, but that's just life. So maybe let me zoom out a little bit so I can see our states. So we have to find W11, and just a quick reminder, W alpha beta, right? This is our wave function in some state alpha and sandwiched with the Hamiltonian with some state beta. So that is what W alpha beta is. So W11 would be simply the expectation value of the Hamiltonian in state number 1. So we need to make sure that we label all of these states. It doesn't matter which one we label with which name, but you have to be consistent. So this will be state 1, this will be state 2, this will be state 3, and this will be state 4. Okay, so now let's begin. Let's go for W11. So W11, what's it going to be? So W11. So this would be this thing squared. So we have to integrate, and we get, well, the square root is going to go away. So 2 pi a times 1 over 4a squared, 1 minus r over 2a squared, e minus r over a, right? Because it's squared, so the 2 goes away. And now, do not forget about this, r squared sine theta. And don't forget about this either. We now have to include our perturbation. So minus e, minus small e, big E, r cosine theta. All right. And of course, now dr, d theta, d phi. Since I didn't specify the boundaries here because I'm lazy, right? It's of course the typical r from 0 to infinity, theta from 0 to pi, phi from 0 to 2 pi. But since I didn't specify, it doesn't really matter in which order I write this down here. Okay, now, what we will do, oops, I moved this. Okay, so we want to, again, save ourselves as much trouble as we possibly can. So could any of this integral of these integrals be 0? So the phi, of course, will not. There's nothing regarding phi, so we will just get a 2 pi. The r might be, but, you know, it's a tough calculation, so I'd rather avoid it. What about theta? Well, in theta, we have integral of sine theta, cosine theta, again, which is the same that we just solved. And we know that this integral is 0. We literally just calculated it. It's right there. So this is 0. So this entire thing is 0. So W11 is 0. So maybe let's zoom in here. I didn't really mean to write it down here, I guess, but, you know, might as well. So W11, 0. All right. Now, what about maybe W12? So state 2 is this one. So what about that? So W12. Now that would be, let's see, so integral of 1 over square root of 2 pi a, 1 over 2a, now times the constants from the second one, so times minus 1 over square root of pi a times 1 over 8a squared. And now let's go for this part. So we get 1 minus r over 2a. Then this r here. So we get r sine theta. Then we have e to the minus r over a and e to the I phi. And of course, minus e, big E, r cosine theta, and r squared sine theta. It's important that you know where each one of these parts comes from, okay? So this part right here comes from the spherical coordinates. This is the Hamiltonian, and then these two parts are simply the wave functions. Okay, so this one looks nasty. So hopefully something here could be 0. So this time there is something related to phi, so let's test it. Let's solve phi integral first. So for phi, our integral is from 0 to 2 pi e to the I phi d phi. So what is this? Now this would simply be e to the I phi over I, and then we have to evaluate between 0 and 2 pi. So here we get e to the 2 pi I over I minus 1 over I. Now, what is e to the 2 pi I? Maybe you know this already. If not, remember that e to the, well, maybe in general first. So e to the I, maybe not theta x. E to the ix is cosine of x plus I sine of x. If you're unsure of where this comes from, I do recommend checking out your courses in mathematical methods of physics. I'm currently working on making a lecture on it on this very channel. So if you're watching this video a few months after release, it might already be up. So check that out. Okay, So instead of x, let's plug in 2 pi. So then we would have cosine of 2 pi, which is 1, plus I sine of 2 pi, which is very much 0. So e to the 2 pi I is simply 1. So we get 1 over I minus 1 over I, 0. So we don't care about the rest of the integral. So W12 is 0. And W21, as we've seen before, is also 0. Right? These are always the same. W12 and 21, the same. Okay, let's now go for maybe W22 or something. Okay, so let me copy the second state, this one right there. So state, oh, there's a little bit of slide in this program. Okay, so W22. So it appears that I made a bit of a mistake while recording the W22 part. So W22 is this second state, and we have to take the expectation value of state 2, Hamiltonian state 2, right? As usual. So what is that? We have all the constants in front, 1 over pi a times 1 over 8a squared squared, and then everything that is inside the integral. So we get this first part squared, r squared e to the minus r over a, sine squared theta, and we get e to the I phi times e to the minus I phi. So that just cancels out, and then we get r squared sine theta from the spherical part, and of course we have to include the minus er vector. But what is r vector? We already know that it's going to have a part in the x direction that has cosine of phi, and in the y direction, or j hat if you want to call it that, it's going to have sine phi, and both of those integrals will be 0. So for that reason, we can just save some time and just write r cosine theta in the k direction. Okay, so this is of course now dr d theta d phi. Okay, so what is this integral going to be now? As usual, the r part we don't really know. We have to calculate that. The phi will just be 2 pi because there's nothing that depends on phi. So the theta integral is the only one that we have to check out. So it's going to be sine cubed of theta cosine theta d theta between 0 and pi. Now this is an integral that we have seen quite a few times already. I'm going to solve it quickly just to show you in case you don't remember. So the way I like to do it is I put one sine and one cosine together, so I can write it as sine of 2 theta over 2. And then we are left with sine squared. But sine squared, that is 1 minus cosine of 2 theta over 2. So here we are now left with the following. So we get two terms. The first one is simply sine of 2 theta over 4. Now this, of course, is going to be 0. When we integrate, we are integrating over sine from 0 to 2 pi, basically, right? Because there's a 2 in here, so even though the upper limit is pi, we are moving faster through sine, so it is the same. You can also integrate it if you want and just see it manually, but we can recognize this right away. Now the second one will be sine of 2 theta times cosine 2 theta, which is actually then going to be sine of 4 theta over 8. And we integrate this, and once again, it's the same. So this time we're going to be going twice through the entirety of sine, but it's simply going to be twice 0, right? So this is 0 as well. So W22 is 0. So the W matrix is ending up quite zero-y, right? There's a lot of zeros. We like that. Okay. Now let's go for W13 and thus W31. Now I think I'm going to go off to the side and right somewhere over here. Let's see if I go down. Do I have don't have that much room? Maybe to this side. Okay, so W33, it's this state right there. Okay, so W33, that would be 1 over 2 pi a, I'm gonna keep the constants outside, times 1 over 4a squared squared, and then we get integral of r squared e to the minus r over, well, 2a, but it's squared, so we get a. And then cosine squared of theta, and now the Hamiltonian, r cosine theta, and I'm running out of space here, r squared sine theta, d3r. I'm lazy, so I'm just writing d3r, which, if you haven't seen it before, d3r is sometimes used as an abbreviation of dr, d theta, d phi, or even other coordinates. It's just a lazy way of writing it. And since I ran out of space, I wanted to use it. Okay. Now, this integral, well, there is nothing related to phi, so the phi integral will give us 2 pi. So nothing too interesting there. What about maybe theta? So what does this integral have in theta? So the theta integral will be integral from 0 to pi of sine theta cosine cubed of theta d theta. Okay, how can we solve this? I think we have seen this sort of integral in the past. So the best way to go about it is to, at least what I like to do, there's a few ways to go about it, but what I like to do is I like to write this, I'm going to go step by step, as sine of theta cosine theta times cosine squared of theta d theta. And now this right here, we can write it as the sine of 2 theta divided by 2, and cosine squared, we can write it as 1 plus cosine of 2 theta over 2. So now we can multiply through, and we get integral from 0 to pi of sine 2 theta over 4 plus, of course, all of this is inside the integral, sine of 2 theta cosine 2 theta over 4. And sine 2 theta times cosine 2 theta, well, that's simply sine of 4 theta. So this is sine of 4 theta over 4. And now you can either see that what we're doing here is simply integrating over the entirety of the sine, which will give us 0, right? Or we can just calculate it manually as you wish. So the first one would be minus cosine of 2 theta over 4 evaluated between 0 and pi minus cosine. So cosine of 4 theta over 4 between 0 and pi. And each one of those will be 0. So the first one is going to be minus 1/4, and cosine of 2 pi, that is 1, minus cosine of 0, which is also 1, so we get 0. And here we have cosine of 4 pi, which is 1, minus cosine of 0, which is 1. So we get 0 minus 0, very much 0. So W33, also 0. Okay, I think I had said I was going to do W13, but I got distracted. But now we do have to, actually, we could do whatever, but I will do W13 now. I think I'm going to get rid of what I have down here. So I'm going to make some room. That way I can remain somewhat close to this. Okay, so W13, and thus W31, because they are the same. So W13, which is equal to W31. Now, W1 is the state 1 is this. So we will have integral of 1 over square root of, I guess I could have written it outside, but it doesn't matter. 1 over 2a. Now let's go for the constants from the other state. So we get 1 over square root of 2 pi a times 1 over 4a squared. Now let's go for the r part. So we get 1 minus r over 2a. Let's leave the exponent for later. And then we have r cosine theta. Now come the exponents, e minus r over a, right? It's squared. And now we need the perturbation of the Hamiltonian here, minus e r cosine theta. And what we have then? Then we have r squared sine theta, dr, d theta, d phi. Okay, now let's go about it as we have done in the past. So there is nothing pertaining to phi, so the phi integral will simply be 2 pi. What about theta? The theta integral will be integral from 0 to pi of, let's see, we have cosine, cosine, sine. So we get cosine squared of theta, sine of theta d theta. Now, how do we solve this? The way I like to do it is use substitution. So we say u will be cosine of theta, du will be the derivative, so minus sine of theta d theta. So thus we can rewrite this integral as integral from, let's see, starting point. If theta is 0, we get 1. And if theta is pi, we get minus 1. Okay, and then cosine is u, so we get u squared du, but with a minus sign. Okay, so let's integrate this. This is simple. It's minus u cubed over 3, evaluated between 1 and the minus 1. We get minus 1/3 of minus 1 cubed, which is minus 1, minus 1 cubed, which is 1. So we get minus 2 times minus 1/3, so we get 2/3. So it's actually not 0. So let's rewrite the expression for 1/3 using what we have found now. So W13, which again is the same as W31. So what is this? We have already solved the theta and phi components. So outside, let's go for the constants. We get 1 over 2 pi a from the square roots. But we are multiplying by 2 pi because of the phi integral. So we can actually get rid of the 2 pi and we get 1 over a. So 1 over a. Then we have 1 over 2a times 1 over 4a squared. So times 1 over 8a cubed. And that's it for constants, I believe. And now we have to, of course, multiply by 2/3 from the theta integral. And everything else we haven't solved yet. So integral from 0 to infinity, it's the last remaining integral of 1 minus r over 2a. Then we get how many r's? 1, 2, 3, 4. So we get r to the 4th here. E to the minus r over a. And do not forget about the minus e. I guess I could have taken it out of the integral, but I didn't see it in time. I'll do it later. Okay. So this is the integral that we want to solve. So let's now just quickly multiply through to separate this into two integrals. In case you haven't seen how this can be solved, that will make it much, much clearer. So this 2 will cancel out this partially. So we get 1 over 4 times 3. I'm lazy. A to the 4th. I know it's 12, but I'm lazy. Integral of 0 to infinity. Oh, almost forgot about the constants again. So this would be minus e. And then inside, let's multiply through. We get r to the 4th, e to the minus r over a, minus r to the 5th over 2a, e minus r over a, dr. Okay. So now we have these two integrals. Now, just in case they don't look quite familiar, let's call this I1 and I2. And let me maybe start with I1, and that will hopefully show you what this is. So I1 is integral from 0 to infinity, r to the fourth, e to the minus r over a dr. So this is something that we have seen many, many times before, but let's use a substitution to make it more evident. So let's say u will be r over a, because that's in the annoying exponent. So du will be dr over a, or in other words, r will be a times u, and dr will be a times du. So this integral will go still from 0 to infinity, right? So if r is 0, u is 0. If r goes to infinity, so does u. And then we have, instead of r, we will have a times u. So we get a to the fourth, u to the fourth, e to the minus u, and then a times du. So we get a to the fifth, integral from 0 to infinity, and u to the fourth, e to the minus u du. And this integral you should already recognize. It's x to some power e to the minus x. We have solved this many times before. In a previous video, this is something you integrate by parts, so I'm just gonna show you how you would do it. I'm not gonna actually do it. I've done it in other videos. If you have been following along, you should already be familiar. But if not, this is how you solve it. So you say, we're going to do this by parts, and you say v is going to be u to the fourth, and then dv is 4u du, and w, or dw, will be e to the minus u, and thus w will be minus e to the minus u. Oh, no d there. And with this, you can, cubed. With this, you can solve this, but you have to do this like 4 times, so it's a little bit annoying. And each time you do it, the exponent drops. So you get 4, and then you get a 3, and then you get a 2, and then you get a 1. So that is why this sort of integral, so whenever you have like integral from 0 to infinity of x to the n e to the minus x dx, so this will be n factorial, and that's it. It's just n factorial. Okay? So that's the result that I will use. So in this case, this integral is simply 4 factorial. So we get a to the fifth times 4 factorial. Okay? And the second integral is quite similar. So integral number 2, so I2, this is r to the fifth over 2a, 0 to infinity, e to the minus r over a dr. So let's do the same change of variables. So r will be a u, so we get integral from 0 to infinity of a to the fifth, u to the fifth over 2a, and then we get e minus u, and then a du. So we get a to the sixth, but we have an a here, so we get a to the fifth again, and divided by 2. And then we get integral from 0 to infinity of u to the fifth, e to the minus u du, which is going to be 5 factorial. So we get 5 factorial divided by 2 times a to the fifth. So that is what we have to plug in. So now going back to this expression, so we get minus e 3 times 4 a to the fourth times our results. So we get a to the fifth times 4 factorial minus a to the fifth times 5 factorial over 2. So let's now simplify this a little bit. So we can, of course, factor out the a to the fifth and cancel with this. So we get minus a. And then we have this 3 times 4, which we can multiply in. So since 4 factorial is 4 times 3 times 2, the only thing that survives is a 2. And 5 is 5 times 4 times 3, those two cancel out, times 2. So we're only left with 5 times 2, and since it's divided by 2, we're left with 5. So this is 2 minus 5, which is minus 3. So in the end, we get 3a EE. So that is W11 and W31. So let's plug it back into this. So 13 and 31. Okay, so I said 3 A E E, 3 A E E. Okay, what about W14, W41? Let's see. So W14 and W41. Now 14, maybe here to this side, just quickly. Okay, so W14. Oh wait, why is it so thick? I need to. There we go. W14. Of course, the same as W41. Now we will get the constants outside. So 1 over square root of 2 pi a and 1 over square root of pi a and 1 over 2a and 1 over 8a squared. And then we get integral with the r part, so 1 minus r to a. And in the 4, get just an r, sine theta. All right. In fact, actually, we can already see where this is going. So maybe we don't even need to write it down, because we have e to the minus I phi. So we can kind of see that it's going to be 0. E to the I phi was 0. E to the minus I phi is going to be 0 as well. Right? Because we're going to get e to the minus 2 pi I, which is, maybe let's move it a little bit. So that's going to be cosine of 2 pi plus I sine of minus 2 pi. Right? And this, of course, has a minus, but cosine is an even function, so this is still 1. Right? So if you are in the complex plane, you can either go in this direction or in the other direction. You end up in the same place. So we get 1 minus 1 over I again, right? Just as we did before. So this is instantly 0 because it has the e to the minus I phi. We don't really need to write it down. Okay, and that's something that we should be exploiting here, that many of these integrals are actually going to be very, very similar to each other. Okay, so I just did 1/4. So let's get rid of this. So this is 0. 0 here and 0 here. So what about 2, 3, and 3, 2? So 2, 3, and 3, 2. That would be these two. But take a look at it. ei phi. Again, instantly, 0. This integral would also be 0 because of the phi part. Like, it doesn't even matter what happens elsewhere. It's 0. No need to even check it. It's 0. Bam. That's why after doing the first few integrals, we can already notice that they're going to be 0. So now we still need 2, 4 and 4, 2. So 2, 4. Now, this one, we don't quite know just yet, because e to the I phi will cancel out with this one. Or will it? Let's see. So let's take a look at this. Now, state W14, or actually, before we even write it down, because maybe we have to think about the whole phi thing, because we're going to take the complex conjugate. Maybe it doesn't quite cancel out. Maybe it's probably going to be 0, but let's see. Is there any chance maybe theta cancels out and we don't really have to think about phi? We don't have to risk making any mistakes. So we said 1/4. Wait, no, 2/4, sorry. I don't know why I wrote down 1/4. We already did that. 2/4. So we would have sine theta. So sine squared. Then we would have a sine theta because of the spherical coordinates. And then we would have a cosine theta because of the perturbation. So in the theta equation, we are going to get sine cubed of theta cosine theta, which is very much 0. Right? We have done this integral before. It's exactly the same as the one with cosine cubed of theta. I think that this is the one we did. Oh no, we did it with cosine. But it's literally exactly the same. You do the exact same thing. The only difference is that here you get 0 minus 0 instead of 0 plus 0 when you substitute sine squared for 1 minus cosine 2 theta over 2. So super 0. It's probably 0 because of the phi part as well, but we don't even need to bother checking that. All right, so W24 is also 0. Whoops. Zoom in. So also 0, also 0. Now we only need to check these three parts. So W34 and W44. So W34 instantly 0. E to the minus IFI all by itself. 0. We already saw that. We don't even need to go further. That's 0. W44. What about that? So in W44, the e to the minus IFI, it would cancel out, right? So that is not really the way to argue it. So let's take a look at the theta part. So in the theta integral, we would get sine squared, right, from here, and then another sine because of the spherical coordinates, and then the cosine. Once again, sine cubed cosine, 0. Right? We have seen this integral many times before. So W44 also 0. So everything was 0 except for the W13 and W31 terms. Okay, so let's maybe rewrite our W down here. So the W, wait, what the? No, I do not want it. Wait, no. Okay, so W13, also actually W, the matrix in general, is going to be, we can factor out 3AEE and just write it as 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0. Okay. There's a fly annoying me. Okay. So this is our W matrix. So if we want to find the energy levels, we need to find the eigenvalues of this, right? So what we have to do is now take this matrix, subtract the identity times, so basically we have this W matrix, only this, we can factor this out. We could leave it there, but it doesn't matter. It's much easier if we don't take it. We do this, take the determinant equal to 0, right? That's what we'll have to do now. So we need the determinant of minus lambda 0, 1, 0, 0, 0, 0, 0. Whoops, I missed one lambda there, so minus lambda. 0, 1, 0, 0, minus lambda, 0, minus lambda, 0, 0, 0. This has to be equal to 0. Okay, so let's take the determinant. Now, the determinant of this, it's going to be minus lambda times the determinant of everything inside, plus the determinant of this, which will be 0, minus, sorry, this is minus, and then plus here. So we get minus lambda times the determinant of this part, which would be minus lambda again, times the determinant of what is inside, which would be lambda squared. Okay, now then we get minus 0 times the determinant, which is 0, plus 1 times the determinant of what is inside. So we basically cover this and this, right? So we get plus this times the determinant, minus this times the determinant. So we get minus lambda, so we get plus lambda, times the determinant of what is inside, which is 1 times minus lambda. So we get minus lambda. Okay, that might be a little bit confusing if you haven't done it in a while, but you have to remember that you're always alternating signs, right? Plus, minus, plus, minus. You cannot forget about that. Okay, so this would be lambda to the 4th minus lambda squared equal to 0. We can factor out lambda squared, so we get lambda squared minus 1 was 0. So from here we see that the eigenvalues, we have 2 for degeneracy for the value 0, and then we have 1, and we have minus 1. All right, so those are our eigenvalues. What does that mean? Well, that simply means that our energies, right, our energies they're going to be shifted. So it's going to be E1 plus one of these times, of course, we cannot forget about the constants that we left outside, right? We still have to multiply this by this amount. So it will be times each one of the lambdas times this. So basically, lambda 1 is and 2 is 0. So the first two states will not really have any corrections, right? So the unperturbed energy, E2, because we're in the second state. So the unperturbed energies plus 0 for the first state. For the second, also plus 0. For the third, we get E2. Then we have plus 1 time A, E, E times 3. So that its energy is actually lifted. And then for the fourth state, it will be E2 minus 3AEE. Okay, so that's what we needed to find. We needed to find into how many levels does it split? Into 4. Well, it's still 4. Actually 3 distinct levels, sorry. So these two have the same energy. So we have 3 distinct levels here, right? We had 4-fold degeneracy. Now we have only 2-fold degeneracy, and then these two states where the energy has increased, right? So we had E2, and then it went up and down, and that part of it also stayed. Okay, so that is the first part, or the second part of the problem. That is part B. So yeah, into how many levels does it split? Into 3 distinct levels. Okay, great. So now we want to find the good wave functions. How do we find the good wave functions? Now, the good wave functions, what did that mean? The good wave functions were those that allowed us to use non-degenerate perturbation theory. Now, what did that mean? That means that basically, because what we are always doing is we want to find the eigenvalues of this W matrix. So if our states are such that our W matrix is diagonal, so that our W matrix is something like, I don't know, alpha, beta, gamma, delta, I don't know, and everything else is 0, then these states are our good states, right? Because then our energy levels are simply going to be the expectation value of our perturbation in each one of these states. So that's what we're always doing when we are doing non-degenerate perturbation theory. So if we have degenerate perturbation theory and we can find those states, then we make life easier for us. So basically, how do we find those states? Well, we have to diagonalize, because this is our W matrix. We want to diagonalize it. Okay, and how do we diagonalize? Well, we have the eigenvalues. So let's do that. So basically what we want to do is we now want to find those states such that our W, or this matrix, right, times those states, so alpha, beta, gamma, delta, has to be equal to 0, right? W minus, of course, our eigenvalues. Okay, so we will do that for each one of the eigenvalues. So for lambda equals 0, we'll have W minus 0, so we get the same thing. So we get 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0. This times alpha, beta, gamma, and delta has to be equal to 0. Okay. I'm kind of running out of space. I'm going to go to the right. So here we just multiply through. So this times this, and we will see each one of the conditions, right? So the first condition is that that's supposed to be gamma. Doesn't really look like it. Is that gamma is 0. The second condition, when we multiply, is that alpha has to be 0. However, there are no restrictions on what the values of beta and delta should be. So they are completely free. And because of the fact that lambda is 2-fold degenerate, we need to find 2 eigenstates that are orthogonal to each other. The only conditions are that the first and third plots have to be 0. Everything else is up to us. But since we're looking for normalized states that are orthogonal to each other, the easiest thing would just be to plug a 1 in here, a 0 in here, a 0 in here, and a 1 in here. That's the easiest solution. So these would be our first two eigenstates, the first good states. Okay, now let's do the same thing, but for the other values of lambda. So for lambda equal 1, for example. So then we would get the W matrix minus lambda. So we get minus 1, 0, 0, 1, 0, minus 1, 0, 0, 0, minus 1. Oh, that's a delta, not a 0. 0, minus 1, 0, 1, 0, 0, 0, minus 1. Okay, times alpha, beta, gamma, delta. Okay, and this has to be equal to 0. So we just multiply it through, again, as before. And what conditions do we get? We get that minus alpha plus gamma have to be equal to 0. So basically, alpha has to be equal to gamma. In second condition, we get beta has to be 0. In the third condition, we also get alpha has to be equal to gamma. And in the last one, we get delta equal to 0. Okay, so we need to find some state where the second and fourth entry are 0, and where the first and third one are the same. So we could go for 1, 1. Right? The problem is that this is not normalized, so we need to normalize this. So the norm of this, of course, is 2, so we need to go for 1 over the square root of 2. Okay? Now, the exact same thing for lambda equals minus 1. So if lambda equals minus 1, let's do it here. So if lambda equals minus 1, then we would get 1, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1. And of course, alpha, beta, gamma, delta. And as before, beta has to be equal to delta, which is 0. Both of them have to be 0, right? From the second and fourth condition. And this time we get that alpha has to be equal to minus gamma. So basically, we need some state where the second and fourth entries are 0, and where the first and third are opposites of one another, right? They are minus of one another. So we could choose 1 and minus 1. And of course, we have to multiply to normalize it. So now we have found all good states. Just to recap, what were all the good states? The good states were 1, 0, 0, 0, and then 0, 0, 1, 0, 0, 1, 0, wait, no. Okay, I'm actually doubting myself. I think that it is like this. 1, 0, 1, 0, and 1, 0, minus 1, 0. So I'm quite sure about the last two ones. Let me see. Okay, no, yeah, of course, these wouldn't be linearly independent. That's what happens when you do this by memory. So this, let me just do it again. So it was 0, 1, 0, 0, 0, 0, 0, 1. Okay, yeah, what I wrote down before didn't make any sense. Okay, so these are our end results. I mean, these are the good states. I'm not going to say end results because we still have a lot of work to do. And by the way, just to make sure that we understand this, this means that this is simply state number 2. So this means, state number 2, which I don't remember which wave function it was. This right here means that state number 4 was a good state. This means that 1 over, almost forgot about that. This means that 1 over square root of 2 times state 1 plus state 3 is a good state. And the last one means that 1 over square root of 2 times 1 minus state 3 is a good state. Okay, so these are the 4 good states. Okay, so that's what these column vectors represent here. Okay, it's very important that you know that. All right, I know this is looking a little bit messy, but let's now go back to the question. So we found the good wave functions, okay? We saw them. It's wave number 2, 4, and the addition and subtraction of states 1 and 3 together. Okay, now we want to find the expectation value of the electric dipole moment, which is this thing right here, so minus E times the R vector, in each one of those good states. Okay, so we want to find those 4 combinations. Notice that the results are independent of the applied field. Well, we will notice that, don't worry. Okay, so I think I'm gonna make some space because this is looking too messy. We don't really need most of these things anymore. Okay, I completely missed that. Okay, I need to actually aim a little bit. Okay. Okay, so let's get rid of that. And maybe of all of this too. All right. Good. So let's go step by step. Now, just as a quick reminder, because I know that I will forget if I don't write it down, our good states are, so state 2, state 4, 1 over square root of state 1 plus or minus state 3. Those are our good states. So our 4 good states. So let's begin with state number 2. So we want to find now the expectation value of the electric dipole moment. Okay, which is actually a very interesting thing because now we can find the electric dipole moment of the hydrogen atom, which is actually quite an important thing to know. Okay, so this will be integral, and then we put the wave function in. So we get 1 over pi a times 1 over 8a squared r squared e to the minus r over a sine squared of theta. Now e to the 2I phi. Let's not forget to put in the minus e r vector in, and of course r squared sine of theta dr d theta d phi. Okay, but what is the r vector? We are in spherical coordinates, so the r vector will simply be, let's put it like this. So it would be r, it would be sine theta cosine of phi in the I hat direction plus r sine theta sine phi in the j hat direction plus r cosine of theta in the k hat direction, or z. So that is what we have to plug in here. So maybe let's move some things. How do I select again? Like this, right? Let's take this, move it to the side, and get rid of this. Actually, there's no way that's gonna fit. Yeah, that was way too optimistic. All right, I need to do it like this. Okay. Still getting used to this program. All right. So let's get rid of this. Plug in this thing right here. And put it back. All right. So this integral, what is it going to be? Now, let's see if anything at all here could be 0. Now, there's one mistake I made. Careful. This right here is 0 because it's multiplied by its complex conjugate. Okay, that's why it was 0 before. That's why it is 0 now. Okay, so that part is 0. Okay, now we have a few things to notice. So again, this is a huge integral. Let's try to find anything that could be 0. We have cosine of phi here and sine of phi as the only elements of phi. What is the integral from 0 to pi, sorry, of cosine of phi, and for sine of phi too, d phi. Both of these are 0, right? You're integrating along cosine and sine along just one iteration. The area under that curve is 0. So yeah, 0. So both of these will actually be 0. So the only part that survives is the cosine part. So what is that integral going to be? So only the theta, or this r cosine theta part, survives. So we would get sine cubed of theta, right? Thinking about theta in the integral. Integral of sine cubed of theta, cosine of theta, right? We have sine squared here, cubed here, cosine here. We have already seen this plenty of times. This integral is 0, right? This is like the third or fourth time it shows up in this problem. So this is 0. So in fact, the entirety of this integral is 0. So the expectation value for the electric dipole moment in state 2 is 0, right? Or in the first good state. Okay, that's neat. I mean, that's nice. We didn't have to work too much. Let's go for the next state. So let's now go for the expectation value of the electric dipole moment, but for state 4, for the second good state. Now, once again, the phi part will cancel out. Let's write all of these constants down, 1 over 64 a to the 4th power, whatever. And then we get integral of r squared e to the minus r over a, sine squared theta, the exponential cancel out. Then we get, again, the vector. So we get r sine theta cosine phi I hat. But actually, we already know that there is nothing else with phi. So actually, why even write this down, right? Both the cosine phi, actually, maybe just to be complete, I'm going to write it down before I say it. But both of these are going to be 0 because of the exact same reason as before. There's nothing else with phi to prevent these two integrals from being 0. So both of them 0, gone, for the same reason as before. So then we get only r cosine of theta in the k hat direction. And of course, r squared sine theta. And let's not forget about the minus e. Okay, so what about this? Well, immediately, sine squared, sine cubed, cosine. 0. Bye-bye. No need to do anything else. All right. So the last state is, of course, going to be the addition of states 1 and 3. So let's go for that one. So the expectation value of these plus or minus states. Okay, I made some room here. So what is that going to be? This will be, let's see, the integral of, now we get states, and this is the thing, we have to take this and square it. Technically, yeah, we're multiplying by the complex conjugate, but nothing here is complex, at least nothing here as an imaginary part, so it's the same as squaring. So we get 1 over 2, and then state number 1, so 1 over square root of 2 pi a times 1 over 2a, 1 minus r over 2a. We can factor out the e minus r over 2a. Then plus or minus, and what do we get? It is, yeah. Then state 3, we get 1 over square root of 2 pi a, 1 over 4a squared r cosine theta. And this thing has to be squared. So when we take the exponential out, we get this. Now let's not forget about the Hamiltonian that we're using. So minus e times the r vector in spherical coordinates. But that r vector, well, we already know that the x and y components, the I hat and j hat, they will simply be 0. So let's go only for the remaining part, which is r cosine of theta k hat. Okay. And finally, r squared sine theta. dr d theta d phi. Okay. So there's a few things we can do already. We can simply pull out, we can factor out the square root of 2 pi a, which when we take it out of this bracket, it will be squared. So we get the 1/2 that is already here times 1 over 2 pi a. We can also factor out 1 over 2a, but when we take it out, it's going to be squared. So we get 1 over 4a squared. And we can also do the phi integral because there's nothing with phi. So simply multiply by 2 pi. Okay, so then integral, and here in the, what do we have left in the bracket? We get 1 minus r over 2a plus or minus. And then we have, let's see, only 1 over 2a remaining, r cosine of theta, right? Yes. And squared, e to the minus r over a. And we have this minus e here, so maybe let's write it down there, minus e. And then we have r cubed cosine of theta sine theta dr d theta. Okay, how can we now move forward with this? Well, we would like to expand this bracket term, right? It is squared, so we need the first part squared and then this part squared. But it's important to note what we would get, right? Because this part squared, it's basically going to give us the same thing that we got when we were simply calculating the expectation value for the state. So basically, that integral from just this term squared would be 1 minus r over 2a squared, and then everything else, right? So we get e to the minus r over a, r cubed. Is cubed correct or did I miss an r? No, I think it's fine. R cubed, and then cosine theta sine theta, dr d theta. But what is cosine theta sine theta? Right? What is that? That is simply sine of 2 theta. Again, one of these integrals that is 0. So the first term is 0. What about the third term, the one we get from squaring this one? So in that case, we get r squared cosine squared of theta over 4a squared times everything else. So there's another r cubed cosine theta sine theta dr d theta. But here we have cosine cubed sine theta, integral of cosine cubed sine theta, another integral we have seen like 10 times. This is 0. So basically, the only term that's not going to be 0 in this bracket, or that could not be 0, we don't really know, that could not be 0, would be the term that is the cross term, right? The multiplication between this and this. So let's take a look at that. Now let's continue here. So this 2 pi will cancel out this here. So we get minus e over 8a squared. And then integral, and the remaining part will be 2 times this times this. So we get plus or minus, right? 2 times 1 minus r over 2a times r over 2a cosine theta. So the 2's cancel out. And then we get e to the minus r over a. This r cubed we can absorb here, so write it as r to the 4th. This cosine we can put here. And sine theta dr d theta. So we can see the theta part will not be 0. And not only that, but this is going to be integral of sine theta times cosine squared of theta d theta, which we have also solved several times already in this video. It is 2/3. So this will be minus e over 8a squared times 2/3. And then we have the integral here. So plus or minus, let's see. Then we can multiply through. So we get on one part r to the 4th e to the minus r over a minus r to the fifth e to the minus r over a over 2a. Oh, I almost forgot about this a here. So maybe let's... Oh, and wait, this is a cubed. Oh, almost made a big mistake. So that's a cubed, and there's another a that's joining, so we get a to the fourth. Okay, almost made a mistake there. Phew. All right, dr. And again, this integral we have already seen. We have already seen it. Okay, so we should know how to solve it. This will be minus e over 4 times 3a to the fourth. Then plus or minus, right, times, just to make sure that multiplying, plus or minus. And this part right here will be a to the fifth, right? Because when we do the change of variables, we get a times r to the fourth. And then from the dr, we get another a. So we get a to the fifth. And this is going to be times 4 factorial, right? We already solved this very integral in this video and in others before. And from this part, we get a to the sixth, but it is divided by 2a, so it's going to be a to the fifth times 5 factorial. Okay, so we can factor out the a's. They will partially cancel out, so we get minus ae divided by 4 times 3, which we can actually take inside, right? So plus or minus is still hanging around there. So 4 times 3 times 2 will only be 2 now. And here we had 5 times 4 times 3 times 2. The 2, 3, and 4 cancel out, so we're left with a 5. So this is minus 3. So basically, what we are left with now is going to be 3 plus or minus 3 a e. We have done it. That is the expectation value. Oh, I wrote a big E for some reason, which is actually a big difference. 3AE. Which is independent of any electric field. We did it. So that is Griffiths problem 6.31. It was quite a bit of using perturbation theory, but I really think that this helps you understand quite a bit better how to use it. A lot of calculations, but that's why it's so important to always look at the integral before you actually start calculating it. Because if you had calculated each one of these integrals, oh my god, that would have been so annoying. But well, I hope this video was useful to you. If it was, make sure to leave a like on the video, subscribe, leave a comment, that really helps with the algorithm, and share this with any classmates that might, find it useful. So I'll see you in the next video. Thank you very much for watching.